So I guess if you need me to read along with you about the work, just have a short review of work in the textbook College Physics by Hughes Young and Philip Adams, then I'm happy to work with you, okay? So let's read this part again to review how to calculate work and work in the physics sense. So what is it? Okay, let me zoom it in a little bit. In everyday usage, work is any activity that requires muscular or mental exertion. Physicists have a much more specific definition, involving a force acting on an object while the object undergoes a displacement. Okay, so I could say that the work that we usually know in our daily life, like, oh, I worked a lot today and I worked a lot to earn for a living. So that kind of work in everyday usage is a little bit different from the way how the work is defined in physics, okay? And here is have to involve a force and some displacement. So let's see how they connected to each other. Let's continue. The importance of the concept of work stems from the fact that in any motion of a particle, the change in kinetic energy of the particle equals the total work done by the forces acting on it. Okay, so let's see. The change in kinetic energy. Oh yeah, we just mentioned the kinetic energy, right? That would be 1 half mv squared, sorry, 1 half mv squared. So the change, yes. Okay. The total work done by the forces acting on it. Oh, so actually this is the content of the work energy theorem that we just mentioned in the previous video. Okay, we'll develop this relationship in, yeah, they just mentioned here in section 7.3. So you can see that that's what we just did in the previous video. Okay, let's come back here. But first, let's learn how to calculate work in a variety of situations. Okay, so let's see how they calculate work in physics. The simplest case is straight line motion of an object acting on by a constant force F. Okay, so in this case, force F is constant. And we have an object, and it's a straight line motion. Straight line motion means that a motion on a straight line. A straight line. Okay. Oh, I guess they have it in here. A straight line. Okay. When the displacement S vector, you see this is a vector. They have a arrow on top of it. So that's a vector quantity. Okay. Whenever you see a symbol with an arrow on it, that's a vector quantity. And force, F, that's another vector quantity, have the same direction. So this is in the figure. Yes, I see the displacement. Okay, so displacement again is defined as an arrow that you go from the initial position to the final position. So we know that if some object has a change in position, it means that it has been moved, right? It has moved. So it means that it's in some motion. So that's why it has some displacement. So displacement is an arrow from the initial position to the final position. Okay? And F here is just like some kind of force and interaction that act on the subject. Oh, can you see that? They try to show that at first the object stay here, and then after being pushed by the force in the same direction to the right with the displacement, then the object got to this point. So it had been displaced by this much amount. Okay. We define the work done by the force as the product of the magnitudes of these two quantities. W equals Fs. Okay, so simply just like times them together. Okay, More generally, if the force makes an angle phi, this is a Greek letter, and okay, let me just note it somewhere here. Okay, phi, we call it as like phi. So it's like a Greek letter. So you can see that in science we borrow a lot of like Greek letters in order to like symbolize for some quantities, just to make the math like shorter. Instead of writing the whole thing like the angle, they just use simple and they use the Greek letter, so we can distinguish with the normal letters, I guess. Okay, so yeah, sometimes it's not very straightforward to know how to say those, but if you want to Google a little bit about the Greek letters, you can see that this one look like a circle with a dash through it. It's a phi. Okay, phi, Greek letters. Okay, if the force makes an angle phi with the displacement. Okay, oh, so that's another figure. Oh, I see. So we have a figure down here, 7.9. So in this case, it's also that displaced, okay, horizontally like this from the initial position to the final position. But in this case, this is the force F, you see? It's not like in the same direction like this one anymore, but it makes some angle. You see the angle phi with the displacement, this one. Okay, then the component of the force along the direction of the displacement is. Okay, so they just care about the component along the directions. Why? Interesting. I'm thinking why. Okay, if I'm the one who read this one, I go think why just that component. Okay, let's see why. Where the subscript. Okay, so it seems that there's two dash like this, right? Yeah, and it seems that these two lines parallel to each other, so it just stands for parallel. Okay, means parallel, indicating that this component is parallel to the direction of displacement. Okay, we can now define work as the product of the component of force in the direction of displacement and the magnitude s of the displacement. Okay, so they try to say like in a simple case that it's just simply F times S like this. But if in a case where F doesn't make it mean it doesn't parallel anymore, but it makes some angle, then it's just the component, the parallel to the displacement is counted into this calculation. Why? Why, right? We have to think the why. Well, I should think about it. If as we know that we can analyze a force as a vector into any components, right? And usually if we can analyze them in a two components, then we try to make these two components like perpendicular to each other, so then we can apply the Pythagorean rules to calculate the magnitude of the force easier, right? So anyways, we usually analyze the force in two components, horizontal and vertical. And think about that. If the car is really a heavy one, it's just moving this way. So if you try to push it this way, in this way, does it help? No, right? Like this component does not help at all in the displacement of the car from this position to this position. So actually only the force, the component, this one is helpful to do the work in this displacement. And this one is not helpful, does not help in the displacement from here to here. So that's why it's not counted. That's why we just care about the components that parallel, in parallel with the displacement. So if the car somehow move in this way, okay, if it's moving this way, then I go say that yes, this component of the force is helpful somehow. But in this case, not at all. It's just moving in this direction. That's why we just care about these components. Let me try to color them in the same color with the displacement. The displacement, and we just care about this part. We don't care about the part that perpendicular to this one. Okay? Okay, so makes sense, right? If something that you still wonder, please feel free to comment in the below, then we can discuss about that.